So welcome back. In this lesson we are going to discuss about quantum states, okay, and measurement, okay, nature of observation, so how it behaves. So we'll understand what quantum state means and what measurement does to quantum system and why observation changes the result. We will be going to observe in this particular video. So moving on to the slide number 1. So that is nothing but quantum state, okay. In classical physics, things are very clear, okay. A light bulb is either on or off. A coin shows heads or tails. It will be a fixed output, either bulb on or off, either heads or tails. But whereas in quantum, things are very different. So every tiny particle like electron, photon, okay, is described by something called a quantum state, okay. It is described by quantum state, usually written as ket psi. This is nothing but ket psi, okay. It represents, okay, we write it as ket psi or psi ket, we can also call it, okay. This symbol carries all possible states, okay, information about that particle. A classical system can be either 0 or 1, but a quantum system can be in superposition of many states, okay. So that is why, okay, we write this quantum state as alpha ket 0 plus beta ket 1. Here ket 0 and ket 1 are nothing but base states like binary 0 1, and alpha are nothing but complex probability amplitudes, okay. So for in the normalization condition should look like mod alpha square plus mod beta square, that should be equal to 1, okay. Moving on to the quantum state, okay. So here let's have one example for equal superposition. So you need to remember this equal superposition, why I call equal superposition. Consider a qubit 1 by root 2 ket 0 plus 1 by root, here one more 1 by root 2 will be there if I write individually, okay, that don't be confused, okay. 1 by root 2 ket 0 plus 1 by root 2 ket 1 I have combined written, so I have took 1 by root 2 common, so that is why I have wrote this equation. So if you take it as separately, then you will be having alpha and beta. So alpha and beta are nothing but 1 by root 2 1 by root 2 equal probabilities. So if you compute the probabilities, that is nothing but mod alpha square, you'll be ended up getting 1 by 2, okay. In the second slide you will be ended up getting 1 by 2. So that is why I have called this as equal superposition. Why I call? Because this is 1 by 2 and this is 1 by 2, okay. So hence there is a 50% chance of to observe ket 0 and 50% chance to observe it as ket 1. That is why we call it as equal, okay, superposition. So now moving on to the definition, okay. So before measurement, the qubit is in both states. So the qubit will be as alpha ket 0 plus beta ket 1, but with equal probability, okay. This is called, we call it as superposition. But after measurement, it will collapse to either ket 0 or ket 1. So after measurement, it will collapse to these two states, either it will be ket 0, either it will be ket 1, okay. So one example I have took, that is nothing but, you need to remember this is unequal superposition. So here I have took ket psi is equal to 3 by 5 ket 0 plus 4 by 5 ket 1. So 3 by 5 is nothing but alpha and 4 by 5 is nothing but beta, okay. What is that? Beta. If I want to get the probability, I need to calculate mod alpha square. So this is the formula. So mod alpha square, if I want to get the probability of ket 0, mod alpha square. If I want to get the probability of ket 1, mod beta square. So if I combinedly do this, I'll be ended up getting it as 1. So it is valid state. So the normalization is satisfied. But if you calculate the individual probabilities, P of 0 is nothing but mod alpha square. If you calculate it, you will be ended up getting 0.36 as a result. But if you calculate the probability of P of 1, this, then you will be end up getting 0.64. In this particular case, they are not equal, so the probabilities are not equal. So if you measure it, the most of time you will be getting 1, because 1 has the more probability. So you can imagine it has a coin slightly heavier on the side, it lands on the tails more often than tails. If the coin is tilted some side, that is nothing but tail side, it will toss every time. When you toss, it will may land towards tails, not head. So that is what the meaning of this particular unequal superposition equation. Okay, moving on to the measurement. Okay, measurement is what makes quantum systems so special. Okay, in normal physics, when you check something, you do not change it. Okay, but when quantum mechanics, when you measure a particle, you change it. Okay, initially the qubit will be at alpha ket 0 plus beta ket 1, but if you measure the probabilities, alpha square plus beta square, okay, when we measure it, it will give one of the two results. Either it will be 0 or either it will be 1. You will be ended up getting only one result and immediately jump into that state. If the result is ket 1, let us say, so that superposition will be collapsed and the information will have only as ket 1. If it is 0, let us see, the information will be lost, the superposition will be lost if you measure it, and you will be end up getting it as 0. So that is what measurement is. So this we can call it as collapse of wave function. Okay, what is that? Collapse of the wave function. If you get 1 when you measure the qubit, the qubit becomes exactly 1. If you measure again, you always get 1 because the superposition is gone. Okay, in classical physics we just find what already done. In quantum physics, the act of observing decides what the result will be. Okay, that is the small difference. So I think in this particular example, if you look at, okay, so I am taking the previous example, 3 by 5 ket 0 plus 4 by 5 ket 1. So you are having the more probability 0.644 ket 1. So the ket psi becomes only as ket 1. So this information is gone, this is gone. So this will only give us ket 1. That is why I said it is the collapse of the wave function. Okay, so I think I already explained all those things. Okay, in classical physics, that is nothing but you will be having only two certain outputs, whereas here mixture of possibilities. Okay, so the nature of observation. Okay, here in quantum mechanics, observation is not passive, that is not like a fixed output, it actively affects the reality. Okay, before we look, the system behaves like wave. Okay, but when you observe it or when you measure it, okay, we call it as observer effect. Before measuring, the system behaves like wave, spread out over many possibilities. That is nothing but alpha ket 0 plus beta ket 1. It has two possibilities. But once you measure it, okay, it behaves like particle. Okay, it is no longer in waves, it behave like particle, fixed to one definite state. Okay, if before measurement the state will be alpha ket 0 plus beta ket 1. After measurement it is becoming either 0 or 1. Okay, the wave function is collapsed. Okay, this will be collapsed and you will be end up getting only this result. Okay, so remember that famous example that I have given, double slit experiment. When electrons pass through two slits, okay, if we do not observe them, they act like waves and create an interference. I am explaining in every class. So if we observe them, they behave like particles, only one slit at a time. So observation changes behavior. Okay, that is what you need to remember. So this shows that in quantum mechanics, reality depends on how we look at it. So the act of measuring is not just finding the truth. Okay, it is actually helping us to create, okay, help us to create some magical things. Okay, that is what we do in observer effect. Okay, So thank you guys. If you are having any doubts, let me know in the comments.